Hi, welcome to Unit 6.1 Kinetics. This is part 1 of 3, and where we are exploring the key questions: what are the factors that influence reaction rates? All right, so what is kinetics? You've heard this before. Kinetics is the study of reaction rates. That's how fast or how slow a reaction is. And this, along with thermodynamics, is sort of one of the two fundamental pieces of information that a chemist needs in order to fully understand a reaction. And both kinetics and thermodynamics are sort of linked by this idea of equilibrium, which is what we learned last unit. So why is it important to study the kinetics? Well, one reason why is that it's used to determine how fast the average person will metabolize a drug under normal conditions. So if there's a certain drug that the average person metabolizes quickly, you're either going to increase the dosage of the medication or the frequency at which the person takes it. And of course, vice versa. Another reason why that's important is because chemists will oftentimes study the kinetics of reactions to figure out, well, how or what are the best conditions for this reaction to occur. So here you see this publication that came out in 2018, experimental conditions affecting the kinetics of aqueous HDN polymerization as revealed by UV-vis spectroscopy. And so what they're doing here is they're using this technique, UV-vis spectroscopy, to study the polymerization of HCN, or hydrogen cyanide, and they're figuring out which conditions will affect the kinetics or rate of that reaction. And chemists will oftentimes do that because if you can control the rate of reaction, sometimes you want a reaction to be fast, sometimes you want it to be slow. You have better control over the reaction in general. Also, sometimes these sort of studies will also lead to information about the mechanism or the pathway by which this reaction will occur under certain conditions. And so that's another reason why kinetics are important. Okay, so we mentioned in the previous slide that there are factors that control reaction rates. What are those factors? There are four major ones that we can control. One is the surface area. If you have a solid reactant, you can break it up into smaller pieces, thus increasing the surface area, and that will have an impact on the rate. The other is the concentration, pressure of the reactant, basically the amount of reactant that you put in. So if you put in a lot versus if you put in a little, that will have an impact on the rate. Temperature is another one, so cranking up the temperature or lowering the temperature will have an impact on the rate. And finally, whether or not you add a catalyst, which this is a term, if you've heard of enzymes before, enzymes are an example of catalysts, and these are things that are basically used to speed up a process. All right, what I want you to do is take a moment to think of real world examples when you try to control a chemical change using one or more of these methods. So have you ever tried to increase or decrease the surface area to control the rate? Have you ever tried to increase or decrease the concentration or amount of the reactant that you use? Did you change the temperature, etc.? So pause the video now and write some real world examples. Think of 2 or 3 to write on the side. Okay, so here are some real world examples that I think of. I love food, so that's usually what comes to mind for me. One example would be mastication or chewing, which sort of speeds up the rate of digestion by increasing the surface area of our food. So we're breaking the food into smaller pieces, and our body is more quickly able to digest and absorb those nutrients. Another one is raising the heat. So when you're cooking, sometimes you'll notice it's not cooking fast enough, so you'll increase the temperature. And so increasing the temperature will oftentimes increase the rate of the reaction that occurs during the cooking process. All right, so how do we quantify a reaction rate? First of all, the rate of reaction is essentially the change in the concentration of a reactant or a product with time. So that's the sort of thing that we're looking for when we quantify it. Now, if you take this reaction here, A going to B, so reactant A going to product B, you could monitor, let's say you want to monitor the concentration of the reactant A over time, and you would get this sort of black curve here. And just a quick note, the shape of the curve will tell you a little bit about the reaction as well. But we'll learn that in a later section of the unit. All right, so for the rate, if you're measuring the change in the concentration of reactant with time, it'll be the change in the concentration of A at time 2 minus time 1 divided by time 2 minus time 1. And that sort of simplifies into delta A over delta T. Now, you'll notice that this slope of this black line here, this plot here, is negative. And that's because reactants are going to decrease over time. So in order to make up for that, we don't want to have a negative rate. What we do is we will take the rate, if we're doing it with respect to the reactant over time, and we will multiply that change in concentration on top there by negative. So we basically just, before we put the negative there, this value, this rate will be negative. So to make it positive, we multiply it by negative. Now, as I said, we can do this with respect to the reactant or the product. So if you were doing it with respect to the product, the rate will be equal to delta concentration B over delta T. No need for a negative here because the products are going to increase over time. So their rates should be positive already. Now, the rate that we see here is like a rate within a certain time frame from T2 to T1. But that's not necessarily the case each time. Like sometimes you want to know the rate at a given time because rates actually do change can change over time. And so in that case, we are going to use the instantaneous rate law, which is essentially the derivative of the curve. So the instantaneous rate is the slope of the tangent line. And if you see here, this red line and this light blue line here, they represent the instantaneous rate. So the slope of this red line, slope of this blue line would be the instantaneous rate. The red line will be like the instantaneous rate at time 1. And for the blue line, it'll be at like between time 2 and 3, closer to time 3. Now, again, for the reactant, you're going to have to slap on that negative there to make it positive. And for the product, there's no need for that. Okay, so these are the two sort of equations that we would use to measure reactant rates. All right, let's try the CFU. You're asked to find the rates of the reaction from 0 to 50, from 0 to 100, and then also instantaneous at 100. And there are two plots given here, one for the reactant, one for the product. You can choose which one you want to focus on. So let's say, for example, if you're doing rate of the reaction from 0 to 50 seconds, and you wanted to use the reactant curve, which is the one that's going down, it's decreasing, of course. So this would be T1 will be 0, and then the concentration of the reactant at T1 is 0.1. And then you go down to 50 here, and you see the concentration is somewhat in between 0.04 and 0.06, so you would have to estimate that value. And then your T2 will be 50 seconds. So those will be your 2 points, and you would take the delta concentration of reactant over delta concentration of time. You could do the same thing for the product, but of course you will be doing something different. So at 0 seconds, you're starting here. So the concentration is 0. And then at 50, it looks like it's also somewhat in between the 0.04 and 0.06. So you would have to figure out. All right, you do that for all three of these, but for the instantaneous rate, you would draw a tangent line, a line tangent to the curve, and then take the slope of that line. All right, pause the video now. When you press play again, the answers will be revealed. Okay, so here's the work for A. If you can do it for, again, reaction or product. Remember, for the reactant, though, you need to have that negative there because you don't want to have a negative value. And so this is my work. My estimations may be a little different than yours, but in either case, you should get something close to a rate of 1 times 10 to the minus 3 molar per second. Notice that the units are important here. The y-axis is in molarity. The concentration is in molarity because it's molar over liter. And on the x-axis is in seconds, so it's going to be molar per second. You have to include the units for rates. Okay, we'll do the same thing. Here's my work. Again, you can use reactants or products. Doing this one, I got roughly 7 times 10 to the minus 4 molar per second. And then the last one for the instantaneous rate, let's starting with the reactant curve. I found the point at 100, drew my tangent line, found the slope, the rise over the run of that line, and I got the rate to equal this. Of course, I'll have to calculate it in a moment. Do the same thing for the product. Drew my tangent line at that point, then figured out the slope of that line. And I actually had to do a little bit more calculation for the slope since it's up higher. But anyway, this was sort of the work I did. And then I got roughly the rate for both cases to be 4 times 10 to the minus 4 molar per second. This one actually came out closer to 5 times 10 to the minus 4 molar per second, but that could be just because of the scale of the drawing. I think these two were meant to be the same. However, rates of reactants or products don't necessarily have to be the same, and we're going to see why that is. There's actually 2 reasons for that, and we're going to explore one now. So let's take a look at this reaction here, the decomposition of nitrogen dioxide going to form nitrogen monoxide and molecular oxygen. Notice that there are coefficients here in this balanced equation. So these coefficients are going to determine sort of how fast one will appear or disappear. So that's one factor. One factor is the coefficient. The other factor is what's called the rate order. We're going to learn more about that later. But now just looking at the shape of the graph, I can tell that these are both the same type, all 3 are the same type of functions. So they're going to have the same rate order. So rate order is not going to be a factor here. The only thing that's going to matter here is their coefficients. So if we take, we focus, for example, on the product side, the rate of appearance of NO is going to be twice as fast for that of O2. And why is that? It's because it has a coefficient of 2, and you can sort of see that in the plot. So the blue line is the concentration of NO versus time, and then the magenta line here is concentration of O2 versus time. You can see the slope for the NO is about twice as large as O2, and that again has to do with the fact that we're making twice as much of it as O2. So how does that sort of affect things? The way that it sort of affects things is that when you're measuring the rates, like let's say you're measuring the rates of NO with respect to NO or the rate with respect to O2, those 2 values are going to be different. And in order to get them to be the same, what you would do, or what you could do, let's say you're looking at the rate of disappearance of NO2, which is our reactant, and you're trying to find the equivalent, you're trying to set it equivalent to the rate of appearance of NO. Since they have the 2 coefficients, there's no need to change. But for O2, since it's going to be slower, you're going to have to multiply it by 2 in order to get the rates to be equal. And that's information sort of like summarized in this blurb here. So you could pause the video now if you want to read through that. And then when you press play again, we will move on to a CFU. All right, so here's the CFU. You want to know what the rate of appearance of O2, given the rate of disappearance of ozone or O3. So pause the video now. If you press play, you'll get a hint before the answer. All right, here's the hint. So what I would do is I would recommend setting up sort of an equation where the rate of O3 is that it equals to the rate of O2, and you're going to have to multiply both of these rates by a value, and the value is going to come from the coefficients in the balance equation. So essentially, which rate is going to be slower? Remember, the slower rate is going to be the one with the smaller coefficient. Just like in the previous example, O2 had a coefficient of 1, whereas the rest had a coefficient of 2. So the rate of appearance of O2 was slower. So whichever one's slower, that's the one you're going to multiply with a larger number in order to set it to be equal. Essentially, it's like flipping or switching their coefficients. So once you have that, you can plug your rate of disappearance of ozone, O3, into this part, and then solve for O2. When you press play again, the work and the answer will be revealed. Okay, so when I did my work, I got that the rate of O2 is about 1.25 or 1.3 times 10 to the minus 2. All right, so that's it for this video. We are going to move